Hello everyone. Sawadee krap. Namaskar. Welcome you all to Plastics News Hour. This is a techno-based program, and in today's news hour, Plastics News Hour, we're having a topic on the design and development of additively manufactured bio-based laminated composites. And this presentation will be given by Dr. Ilaria Papa. She's a professor at the University of Naples, Federico II, based in Italy. So before I let her to give a presentation, let me introduce to you all to the Plastics News Hour. This is a regular online program for the global plastics industry, where you have technical talks, panel discussions, and business conversations related to the plastic industry. This is hosted by Technobase. Technobase is based in Thailand, established in 2005, and it is recognized as International Resource Center for Polymer Processing Industries and also the processing and manufacturing technologies. You can find more information about Technobase at technobase.org. Just give you some overview about the Technobase. We are specialized in the polymer industry. We address on the rubber, plastics, polyurethane, adhesives and coatings, and also a little bit on the non-polymer on energy, environment, membrane and filtration, recycling and recovery, and the nanotechnology and smart manufacturing. Our main business, our main focus is always on the professional education, 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 education. That is our mantra, and where we trying to educate professionals so that they can do their jobs better. So we have online professional programs and also in-person programs. We also offer some specific diploma programs for the industry, and we have publications also. Along with the professional education, we do offer various business services. Today, actually, this program, Plastics News Hour, is also one way of education. And okay, this is we update you on a regular basis. When it comes to the business services, we host conferences, exhibitions, virtual events, webinars, road shows, networking events, technical and business consulting, factory and process audit, and also the marketing and branding. We have various types of news hours. You can see we focus on various polymer industry, rubber industry news hour. We have plastics news hour. We have PU news hour. We have advanced technology news hour, and also the latex industry news hour. So various types of news hour we have and on the regular basis for the benefit of the industry, so that they get updated on the regular basis. Let me give a quick intro to the various activities that we do offer for the Technobase, that we offer for the plastics industry, where our services are pretty much global. Okay, this is the first introduce of the news hour. This is it started only recently. Okay, this year only. We'll be inviting many experts like Dr. Papa and many others will be regularly contributing the various developments in the plastic industry. Just give you some glimpse of various experts wherever they are, who are willing to share, update information with a research side, whether it's industry point of view on the recycle, you name it, processing side and new materials. So we cover a broad range of subjects that is relevant to the plastics industry. Some of them are researchers, some of them are consultants, some of them are technology supplied itself. So it's a great opportunity for all the people to learn on a regular basis through this plastics news hour. We have trade exhibitions, which are focused for the plastic industry. One is a Plastic Extrusion Expo we are hosting in March, and also we have Rotomolding Expo. This is a specialized exhibition focused on the rotational molding. We're doing this one in Bangkok as well as in Sharjah near to Dubai. And we are also introducing a Polymer Laboratory Expo, where we focus on the certified polymer laboratories and also the testing instruments. So there are three types of events, and we have other things, the recycling and recovery as well. Where we offer various booth options to exhibit, and we do another, as I mentioned to you, training education is our key, and we believe in totally on that. Professional education is very important for the growth of the industry. So we have for the focus on the plastic industry, we have worked with a lot of experts from the different parts of the world offering this professional education. Some of them are available now online, and they are covering various subjects, design, injection molding, and also we have film extrusion, even the polymerizations as well. But we'll be adding more subjects on the regular basis with working with experts across the world to train the workforce of the plastic industry. So these are the subjects. So please do check our website technobiz.org, and if you'd like to know about one thing I want to specify here is that we have a very extensive training modules for the rotational molding people who are interested to know about rotational molding. We have other programs called Plastics Connect. This is a digital marketing for the plastic industries and technologies who want to promote their products and the technologies. So we offer various memberships, okay, platinum, gold, and silver membership. You need to we promote their videos or interviews or presentations in advertisements or the news developments or newsletters, all kinds of things we promote through this Plastics Connect program. Anybody interested, you can always contact me. So that's about the Plastics Connect. We do also the Plastics Tech Talks. This is a customized in-person or in-person also an opportunity where you can introduce your technologies or promoting a specific areas of the plastic industry. And especially one thing I want to hear is a rotational molding network, which is a specific network for the rotational molders. And we have specific programs for them, exhibition, education, management, leadership, in various areas of it. Okay? But that's about it. That is what is all about Technobase. It's basically we are a resource center for the polymer industries, and you can always check details about Technobase at the technobase.org. So, if you feel free to reach out to me if you need more information on the Technobase. So now we are all here for the topic. Today's topic on plastics news hour is the design and development of additively manufactured bio-based laminated composites by Dr. Ilaria Papa. She's a professor at the University of Naples, Federico, to Italy. Before I invite her, I'd like to brief about her expertise. She has expertise on impact, behavior, and damage investigations of the traditional innovative composite materials, non-destructive technique on traditional innovative materials, additive manufacturing of polymer materials. She also conducted research on the innovative biodegradable and renewable filament materials for additive manufacturing and improvement of the composite materials manufacturing process. So she's very specialized in this area. It's a great opportunity to have Dr. Ilaria Papa, a professor at the University of Naples, Federico, to give part of this news hour, and let me invite her to give a talk on the design and development of additively manufactured bio-based laminated composite. So let's invite Dr. Ilaria Papa.
Hello everyone, good afternoon. As I just introduced Param, I am Ilaria Papa. I am an assistant researcher in industrial product and process engineering at University of Newport, Federico II. My main area of interest is about the characterization and the impact behavior of composite materials and non-destructive technique, but recently my research interest has focused on the possibility to produce and to characterize innovative composite laminates based on resin and reinforcement biodegradable or coming from renewable sources. Today, I'm going to talk about the design and development of additively manufactured bio-based laminate composite. And with this presentation, I would like to address three main topics such as sustainability, polymer additives, and polymer recycling. It's certainly a broad and complex discussion, and therefore I will mention the problem by showing you some results of my current research. Plastic material, natural or derived from renewable sources, have attracted, of course, extraordinary attention as they don't contribute to depletion of fossil resources, ensure a reduced production of carbon dioxide during synthesis and transformation, and therefore generate a lower environmental impact than conventional ones derived from petroleum. So in this context, recently with the aim to meet increasingly ambitious environmental requirements, Especially interest has been devoted to potential offered by so-called green resin as bio-based polyester or polyamides, many of which already diffused even in different industrial fields, from packaging to biomedical, from textile to automotive, and so on. Specifically, the implementation of adequate chemical and or physical modification procedures, such as the addition of appropriate additives or reinforcement, permit to successfully overcome new challenges, essentially due to expected lower thermal stability and inferior mechanical performance with respect to the conventional petrochemical polymers. Among the synthetic bio-based polymers, a special place is undoubtedly reserved for polylacticid, or PLA, as it is known, which in recent years has aroused the interest of a lot of researchers, becoming the subject of thousands of publications available in the literature. PLA, as you know, is one of the most widely used bioplastic, but its intrinsic characteristics, such as fragility, often limits its use, in particularly demanding applications unless strategies such as mixing with other polymers, or the inclusion of suitable additives that are taken into consideration. With this approach, new environmentally sustainable materials with adequate performances and ensuring the reduction of environmental combination associated with plastic are produced by industry, but also by a lot of researchers. The most common technology to transform thermoplastic-based green composite on industrial scale are extrusion, compression molding, injection molding, and the success of these processes depends on the perfect knowledge of the chemical, physical transformation undergone by the raw materials, and it often does not exclude the use of specific preliminary treatments or subsequent finishing processes of the parts produced, both costly in terms of time and expense, and which often reflect in the accumulation of production waste. So the technological challenges of that can arise from the use of alternative and more sustainable materials can be alleviated by a more rational use of the same, as well as by the elimination of additional post-treatment steps, thanks to the use of additive technology that you can see in the slide. Among the latter, the fused deposition modeling, or FDM, is the most common approach for processing the thermoplastic formulation. In practice, the process involves a filament of a thermoplastic material, which is heated and passes through a nozzle to be deposited according, of course, to a preset code onto a plate, a different material that we can see in the second part of the presentation. The production of an object takes place by superimposing layer by layer of the material, which gradually cool and solidify one top on the other, according to a typical layer by layer arrangement. Nowadays, FDM has already gained a relevant interest in several fields of application, as aerospace, automotive, medical architecture, food, design, and the market demand for the printing filament is expected 3D experiences an annual growth rate of quite 20%. So that said, taking into account that the raw materials for the production of filaments are still many of petrochemical origin, also in this case there is a growing interest in biocomposite, for example in the potential of alternative filaments based on green matrices. Perhaps modified by the inclusion of natural additives, for example, reinforcement, as I said before, and as vegetable fibers or agri-food waste. To overcome the inevitable environmental impact generated by the traditional plastic waste, which often cannot be recycled, in recent decades, a growing interest has also been directed to the study of the bioplastic materials. Of course, in literature, many studies have investigated the mechanical properties of PLA parts manufactured by different technology, but also by FDM. Since the high know-how of PLA, but only few studies have investigated the energy consumption during the FDM process. So a part of this talk is about understanding how to optimize the process parameters to obtain a good mechanical properties of PLA parts and minimizing the energy consumption during the FDM process. Another part is about to meet increasing ambitious environmental requirements. And so what kind of innovative green resin we can use and how the properties of these materials can change after recycling. So start to discuss of sustainable materials and energy consumption. Currently, the large use of the 3D printers establishes some issues by considering the environmental impact of home activities. A sustainability perspective suggests developing new ways for 3D printing parts in energy-saving approach. In a previous research study, it was observed that the greatest contribution in terms of energy consumption is given by the heating of the plate and the continuous cycles to keep it warm. So as a matter of the fact that the power spent to heat the plate is at least 16% of the total power demanded by the machine. And for the conventional plate made by steel, the thermal dispersion forces, the system to keep the power on for the whole printing cycle, because the bed has difficulties to reach the target value, in particular when it is too high with respect to the room temperature. So in this scenario, the design of the plate was considered very crucial to pursue the energy consumption reduction on large-scale device use. The main topic investigated in the literature is the influence of the plate temperature on the mechanical properties of the printed components, and also its influence on different extruded materials. In other words, the plate shrinkage and the correlation with the workpiece dimensional accuracy were also evaluated. And also the possibility to use a new material for the plate was investigated with aim to improve the mechanical properties. In any case, each optimization was not related to the energy consumption evaluation and also the influence of the plate material on the mechanical properties was neglected. So for the purpose of the research of my group is also to optimize the energy consumption by preserving the mechanical properties. In this slide, I want to show you about how to optimize the process parameters to obtain good mechanical properties of PLA parts, minimizing the energy consumption. In my department, I said we have carried out some research about this topic using a particular PLA, since of course we have a lot of know-how on this material, but it could be very interesting using also other materials. So on the basis of I said before, the experimental study was carried out considering the steel standard plate of the 3D printer as a reference and other plates for the investigation of the specific thermal properties. The heat input quantity required was analyzed in terms of power absorbed with the aim to evaluate the energy consumption. In the slide, we can see the experimental setup that consists of an intermediary connection between the 3D printer and the electrical cabinet. On the right, we can see the 3D printer adopts, and on the left the electrical cabinet. In the center, the power analyzer we used to measure the energy consumption during the process. The analyzer was connected to intermediary connections by means of two tension cables, and the current sensor as an electrical connection of the 3D printer is monophase with a neutral. And so in this slide, we can see the experimental plan of this part of the research. We fixed the plate temperature equal to 19 degrees to keep the material fluid and reduce the voids. That is a very issue of this technology, as you know. We varied the two levels of the extrusion temperatures and also the speed for a total of 4 configuration. So the speed is 17 and 110 millimeters per second. Also, 3 tensile specimen as standard suggesting were printed and tested for each configuration. An important thing that I have to say is that all the samples were printed, either use an aluminum plate and steel plate, compare the results obtained, and so to study the effect on the mechanical properties, but also on the energy consumption. In red, in this slide, we can see for the steel and aluminum plate, the power average during the main subphase. Power average during the printing subphase is very similar comparing steel and aluminum plate, but by fixing the same process parameters, printing subphase results less time by using the aluminum plate due to the higher thermal conductivity. Of course, power average as well as the duration for bed heating are higher for steel plate than the thermal conductivity of the steel. Here we can see the power trend of the same configuration during the FDM process by using the steel plate and also the aluminum plate. And we can see immediately that is the bed heating lasts less using the aluminum plate than the steel plate. This result is due to the fact that the thermal conductivity of the aluminum is higher than that of the steel plate. Moreover, by observing the printing surface of the diagram, we can see that the average power during the printing with the aluminum plate is lower than that using the steel plate. So we in this slide, in the P charts, we show a decrease in the bed heating. contribution and an increase up to 70% of the energy spent for printing phase, which is the only value added phase, because just in this phase the workpiece is built. The same behavior is reported in phase duration P charts. The rapid, as you can see, the rapid heating of the aluminum bed plates allows the increase of the time percentage spent to print the component. Nevertheless, the printing time is independent from the capacity to reach and to keep the target temperature, because it depends just on the nozzle speed. So the significant differences reported by the energy spent is even more important, since it means that although the duration of each phase doesn't change, the energy spent is improved. The last is due to the numerous on-off heating cycles during the printing phase that we have seen in the previous graphs, where we can see the signal go up and down. This phenomenon indicates that the 3D printer continuously requires energy to maintain the steel plate at 90 degrees, differently from the aluminum plate, according to their different thermal properties. Thus, in this part of research, we have note that it's better to use an aluminum plate for the desktop 3D printers rather than steel plates, to reduce power and energy consumption of the RFID process, and its fact is related to the conductivity of the material, of course. From the values resulting from the energy consumption analysis, was performed analysis of the specific energy consumption, or SEC, that we can see in the slide, which is highly used in the literature as a key sustainable performance indicator. In particular, in the FDM process, SEC represents the energy consumption for printing the mass unit. Exists a linear correlation between the SEC and the printing time, as expected, and so a new efficiency index given by the ratio between UTS, that is the tensile strength of the component printed, and SEC was evaluated. The index explains numerically how higher the tensile strength is obtained for unit-specific energy consumption in FDM process. So a higher value of this ratio indicates a better process efficiency for the printing strategy. And this figure shows the variation of this efficiency index by varying the printing strategies reported in the x-axis. Using the aluminum plates, the square point, using the aluminum plates, the best performance in terms of tensile strength for specific energy consumption has been observed with the strategy with higher value of scan speed, 110 millimeter per second, and one level of temperature equal to 215 degrees. Conversely, the worst case has been observed with the strategy with a lower scan strategy, 70 millimeter per second, and one level of temperature. So the better plates to print results not the aluminum, as said previous, but the steel one, that reduce the power and energy consumption during the effects of mechanical features. The topic the topic that we have discussed regard the technological and environmental sustainability of 3D printers, that is very important for the industrial application in a sustainable perspective and energy efficiency. So we have studied and evaluated to define a correspondence between the main FDM process conditions and efficiencies of this technology, evaluating its performance in terms of both quality and energy consumption. The effect of different printing plates and different materials on the energy consumption in FD process correlated to the quality of the parts has been investigated, and we can say that the average power during the printing surface is lower by using the aluminum plates than the steel plate, but this result allows saving energy even during the printing surface of the FDM process. So it's finished the first part of our discussion, but we can start to discuss about biodegradable and green materials. As I said before, we know that the plastic, natural or derived from renewable resources, have attracted great attention, as they do not contribute to depletion of fossil resources and ensure a reduced production of carbon dioxide during synthesis and transformation, and therefore generate a lower environmental impact than conventional ones derived from petroleum. So in this context, with aim to meet increasingly ambitious environmental requirements, a special interest has been devoted to potential different green resin, many of which already diffused even in different industrial fields. Specifically, the implementation of a dedicated chemical or physical modification permitted to successfully overcome new challenges, essentially due to expected lower thermal stability and also inferior mechanical performance with respect to the conventional petrochemical polymers. As I said in the first part of the presentation, the technological challenges that can arise from the use of alternative, more sustainable materials can be alleviated by a more rational use of the same, as well as by the elimination of additional post-treatment, thanks to the use of additive technologies. Among the additive technologies, the fused deposition modeling is the most common approach, as I said before. In practice, you know as that it molds the filament, the thermoplastic filament that is added and passed through the nozzle. And so by a code that we have before discussed, according to a typical layer by layer arrangement, the parts is produced. But the great interest of the market demand for the printing filaments give the researcher to produce other type of filament. Taking into account that the raw materials for the production of filaments are still mainly of petrochemical origin. Also, in this case, there is a growing interest in biocomposite, in the potential of alternative filaments based on green matrices, perhaps modified by inclusion of natural additives as vegetal fibers and agri-food waste that are not present in the market. And so it is starting a very great research in innovative, biodegradable, and biocomposite filament to use in the 3D printing. PLA, although attractive from an environmental point of view, is often modified by mixing with other resin or the addition of fillers, with the aim to counterbalancing some of its intrinsic critically characteristic, such as fragility, low melt strength, and relatively low heat resistance, and high cost. In this regard, for example, results obtained by adding PLA with wood floor, that in the slide we indicate on WF. Important sources of renewable biomass are available. For example, the talc is normally used together with the wood floor with a percentage of 13% in weight in order to improve the mechanical properties of the compound and to improve also the coupling between the polymer fibers and other particles. Suitable coupling agents are usually used. The literature reports results relating to the characterization of a composite prepared by mixing in the melt state, so in the extrusion, and containing different percentages of powders. As you see in this slide, an increase in young modulus was observed in correspondence with an increase of wood floors, while the best performance is obtained with the compound containing the PLA-WF talc, that is the coupling agent. So the behavior is in the presence of the sealant improves compared to the compound of PLA and WF only, the net one. As far as the tensile strength is concerned, the best behavior is obtained for the PLA, WF, talc, and 1% of sealant. Therefore, the presence of sealant improves the compatibility of the PLA matrix and the wood floor and the talc. And so, as in the case of young modulus, but only for 1% of the sealant. It is therefore observed that the use of natural fibers can lead to improvements in mechanical properties compared to the PLA, but the difficulties of coupling the PLA matrix and fibers are now the main obstacles to overcome to obtain wider application. In fact, other researchers are present in the literature because the cost of mixing PLA with the synthetic macromolecules is high, and therefore lower cost options such as natural biopolymer materials, like in this case bamboo floor, are interesting. Bamboo floor is composed by a natural polymer that is also recyclable, and as a type of natural plant fiber, bamboo has the characteristics of low specific gravity and good mechanical properties, as well as low cost and also abundance. In addition, the surface of BF, so bamboo floor, can be modified before blending to improve its interfacial compatibility properties with polymer resin. To improve the coupling between the PLA matrix and the natural fiber, a study at the University of Virginia Technology and Business University used the GMA grafted onto PLA to improve the compatibility of PLA and bamboo floor. And as you can see from the graphs, from tensile test, bone tensile strength, Young's modulus first increased and then decreased with increasing coupling agent. In particular, we can see recorded a 44% increase in tensile strength and a higher increase equal to 155% of modulus Young versus agent-free compound. The presence of the coupling agent in this way it's possible to obtain a less expensive compound using renewable and biodegradable biomass. And it led to a close bond between BF, backbone floor, and the PLA matrix, thanks to the improvement in the mechanical properties of the compound that is observed, and respect to the features of the neat PLA. In addition to using the renewable biomass, other research has also focused on the use of natural fibers as the products typical of the areas, as in the case of the waste deriving from the milling of olives studied at the pillars by the Miran University of Beji in Algeria, in order to have a cheap, locally available component and avoid having to dispose of it by incineration. As you can see, the samples are formed by PLA and olive flour at 20% in weight. The compound has first undergone an extrusion process that it has been pelleted. Finally, the samples for the mechanical test were obtained by the injection molding technique. Some of the samples were subjected to accelerated aging treatments in order to study the characteristic of the compound in different phases of usable life of any products. And I haven't shown it in the slide, but from the DSG analysis, it's observed that the pure PLA samples have an higher melting temperature after accelerated aging, given the abritment of the surface following the process, while the compounds, whether treated alkaline or not, the temperature decreases. Finally, the samples were subjected to tensile test also in these research, and it was observed that the samples PLA with olive flour or OHF compound showed an increase in the Young's modulus, and in particular, the treated samples show this increase. Following the aging process, there is a deterioration of the mechanical properties of the samples, but it is observed that the treated samples have a better behavior and therefore a lower loss of mechanical strength compared to the untreated samples. That said, we want to show also my contribution, the contribution of my group in the slides, that is focused on the formulation based on a commercial polylactis resin modified by the inclusion of food floor waste up to 5% by weight, and compares the performance of the products of the samples obtained with the conventional technology as compression molding with those made using the 3D printing, with the aim to of enhancing the benefits of one process over the other. We have printed and also obtained by a compression molding specimen from the different basic formulation indicated in this slide, and were experimentally compared by thermal, mechanical, and morphological analysis. As you can see in this graph, you can see the behavior of innovative film that we have produced during our research of all the materials extracted, and the filler promotes, as you see by this graph, the filler promotes a significant increase in material strength, but in particular, this effect holds true for specimens obtained by compression molding, but appears to be reversed when the filaments are transformed by FDM due to the important issue correlated to the innovative technology. In fact, we can see that the preliminary results emphasize that through compression molding, so the CM sample, it was possible to get homogeneous components and the natural infilled used as reinforcement, improving mechanical performances. For the additive technology, so the 3D samples, the samples obtained show a lower mechanical behavior and underline the technological issues of the technology. In fact, the main results obtained on the 3D printed specimens show that the younger models and the tensile strength of the composite specimen are mainly worse than those characteristic of the neat PLA, that is this black for the both technology, that's the black line for both technology in this graph. This variable could be due to the raster angle of the deposition equal to plus minus 45 degrees. So during the printing process, the floor waste particles don't align along printing orientation, as also demonstrated in other literature indicate on the website. And on the other hand, the assembly of filaments in FDM cannot prevent holes between filaments, the superposing of filaments, reducing the mechanical properties. Under small process conditions, this effect is expected to be greatly reduced for compression molded, as the samples are subjected to high compaction pressures during the production. So I have shown you 3-point bending test results, and even if in this case the CM samples with compression molded parts with the same floor weight content show higher maximum load and modulus values than those obtained by FDM, thanks to the better compaction. In particular, for the compression molded parts, a higher value of the maximum bending load is recorded with respect to the reference knit matrix, the black line, but this parameter doesn't vary significantly as the filler contact varies. On the contrary, we can see here, for the samples obtained by the tray printing, the filler seems to have a non-monotonous effect on the maximum load, and in any case, not significant compared to the matrix one, that is, in this case, the black one. Unlike the tensile results, for the samples containing 1% of floor weight, that are the red line, a notable performances improvement was recorded. Static and bend tests indicate also in the breakage failure that the failure in all composite systems tested occurs due to the activation of the compression failure mechanism on the upper surface of the specimen, and this behavior in the case of the 3D samples obtained with 1% of floor weight helps to overcome the limits of the technology by compressing the presence of voids in the section. However, as the floor content increases, the not homogeneous distribution of the filler leads to a worsening of the mechanical behavior of the material. So the second part is finished, and so start to discuss the last and third part of our talk. It's about the recyclable materials. Currently, we know that the large use of desktop establishes some issue by considering the environmental impact of home activities. And of course, a sustainable perspective suggests developing new ways for the 3D printing parts. The problems of biodegradability and recycling of the most commonly used plastic materials, up to now have led to research focusing on the identification of new types of biodegradable plastic, such as the PLA. We remind that, of course, biodegradability means the ability of a material to be degraded in part or completely by microbial species present in the environment when found in particular environmental conditions without releasing toxic products. The product of the biodegradable portion of a material in carbon dioxide and water, it must be considered, in fact, that due to the great variety of elements present in biodegradable plastics, only a portion of the latter is truly biodegradable. Of course, these plastics are spreading more and more within society, so much so that in the near future it is expected that they will become a considerable fraction of plastic waste, which must be appropriately managed. A first way of doing this is to accumulate waste in landfills, but in the case of PLA, a large number of alternatives to this process are available. In fact, it is possible to trap PLA in composting plants, and it is possible to proceed through mechanical or chemical recycling, or it's possible to burn waste in incineration plants to obtain energy. Among all these possible alternatives, one of the most important is certainly the mechanical recycling, which makes it possible to recover waste PLA and reuse it as a raw material in forming processes in order to obtain new products. One of the main problems of this process is the inevitable thermomechanical degradation to which the material is subjected due to the conditions to which it is subjected during the life cycle and during the recycling. This degradation causes the mechanical, thermal, and rheological properties of the recycled material to be different from those shown by the virgin or neat material, and often making it impossible to use the recycled material for the same application for which the virgin one was used. For this reason, the effect on PLA of physical treatment, such as thermal annealing, the use of antioxidant stabilizer and chain extenders, the creation of blends or composite materials are being studied. In particular, in the part of the results obtained that I want to show you, the effect of adding a chain extender to the PLA subjected to various mechanical recycling treatments and the mechanical bend extents can be studied. And usually plastic waste in PLA is treated through mechanical recycling, but when its properties become such as to compromise its possible future application, other ways are preferred, as composting, incineration, or chemical recycling plants. So PLA is currently used to make a larger number of disposable consumer products, such as cutlery or tableware, for warps, for kitchen appliances, computers and portable devices, for compostable bags, and also for food packaging. Furthermore, PLA is one of the most used materials also for filaments in the world, and it's filaments for 3D printing, and it's also used in automotive sector for mats, panels, and covers in 3D printing, thanks to its low melting temperature. The mechanical recycling of PLA was the subject of several studies conducted in the laboratory, during which the recycled materials was analyzed from a morphological, structural, rheological, and mechanical point of view in terms of the release of low molecular weight compound and through specific analysis technique for the possible fit of application of the PLA and also of the recycled PLA, such as mass transport or its use based on the dielectric properties that characterize it. In this slide, we show a research of Badia et al. We can see in same images of the surface of dog bone specimen of virgin PLA, and PLA worked 5 times by injection molding. The micrographs show a loss of orientation of the processing line recycled PLA, which is present instead in virgin PLA. Furthermore, the surface is less smooth and more prone to mechanical scratches. Then the figure shows the effect of 5 injection cycles and 10 extrusion cycles on the mechanical properties of the materials in terms of tensile strength and toughness. An analysis of the stress strain curves obtained from the tensile test shows that after 5 rework cycles, the Young modulus didn't change significantly, is the same, as well as the ultimate strain and tensile strength. Failure to analyze other parameters could lead to misleading conclusions about the effect of the mechanical recycling on material properties, which is why the results of other tests should also be analyzed. It is possible, in fact, to study the link between the mechanical and rheological properties of the material by analyzing the variation of toughness and melt mass flow rate, the MFR. It's indicated in the axis of this graph, with increases with the number of recyclists. In particular, the figure shows that the MFR presents small variation between the first cycles compared to the value shown by the knit material, the virgin material, while as the cycles increase, these variations become more and more significant due to the decrease in the average length of the chains, which leads to an increase of smoothness. And then also the figure also shows a significant decrease in impact resistance as the number of cycles to which the material is subjected increases. Also, my working group undertook this study. In particular, we have evaluated the effect of adding a chain extender, that is a layer peroxide, to PLA subjected to various mechanical recycling. So we have the knit PLA materials recycled 5 times, the knit one recycled 1 time, 2 times, 3 times, 4 times, and also the additive ones recycled 1 time, 2 times, 3 times, and 4 times. And in this case, we have recycled the PLA filament and reutilized in the 3D printing, and realized also the additive filament for the 3D printing, recycled it 5 times. Also in this case, for the additive manufacturing technology, we can see a decrease of all mechanical features obtained we can see in this slide, obtained as the number of recycling cycles increases. In particular, we have a lower value obtained by the additive ones, but a more strain indicates a more propension to less propension to damage of these components, and of course by dependency of the line we can see that the modulus and the mechanical feature decrease as the number of the recycle operation increases, and this happens for both neat and additive PLA. I have shown also you these samples to show the change of the breakage, the failure breakage of the flexural test after five cycles of recycling, and that's all. So thank you very much for your interest in this talk. I hope that the information I have provided has been useful. And if you want, you can ask me a question by writing to my institutional contact, it is, or you can follow me and write me a private message on my ResearchGate and LinkedIn profile that I have reported in the slides. Thank you very much.
Thank you very much, Dr. Ilaria. Excellent presentation, very informative.
Thank you.
Appreciate the participation in this plastics news over today. And I hope to invite you in the future programs of the Plastics News Hour. Thank you very much for being part of the Plastic News Hour today.
Yeah. Thank you. Bye.
Bye. Guys, that's the end of the Plastic News Hour today, focusing on the design and development of additively manufactured bio-based laminated composites by Dr. Ilaria Papa. She is a professor at the University of Naples, based in Italy. I really hope that you find this presentation useful to you. And if you have any questions, as Dr. Ilaria has mentioned, please reach out to her either by email or to connect through their LinkedIn or ResearchGate as appropriate. Thank you all for joining this session. If you have any questions, I'd like to reach out to me. You can always contact me at this contact number on emails and WhatsApp, whichever is convenient to you. And I see you in the next episode of the Plastics News Hour. Thank you all. Bye-bye for now.